All right, thank you. My name is Ravi Kumar, and I'm going to talk about dynamic pricing, in particular for ancillaries for airlines. And this is joint work. This is joint work with Guangrui Shi from Virginia Tech and a couple of my colleagues, Ang Lee from Pros and Yanshu from Pros as well. Okay, so because we are switching topics, let me start by explaining a little bit about dynamic pricing and traditional dynamic pricing systems. So a lot of these systems are governed by these models which estimate price elasticities or purchase probabilities. For example, here is a figure which is showing for any given price, what's the probability a consumer is going to, what's the probability a consumer going to buy. More recently, so given a purchase probability, you can then find an optimal price by maximizing the profit. So that's a unimodal problem and it's easy to optimize. More recently, people have focused on something called as dynamic pricing. So they have refined these purchase probability models to add context and additional information, right? So these contexts could be product features, competitor features, events, and customer features. And now for each different context, you have an optimal price. But most of these models rely on the fact that you have sufficient price variability in the sales transaction data, right? So that you can estimate your price elasticity. But there are certain situations where there is no price variation. For example, if you have a new product, right? So you have not offered it in the past, you have no data to estimate what the price elasticity is. Or if you have been offering a product at a constant price, so there is no price variability in that. So what to do in these situations? Right, so consider this situation where a product was historically sold at a fixed price. There was no price variation. These static prices are often not optimal. They come about by some business rules. And the traditional approaches for estimating demand functions or purchase probabilities are difficult to implement because there's no price variability. Now, in more and more such situations in modern times, because data is becoming larger, the seller now wants to implement a system which computes revenue optimal prices, right? And also want to include contexts, right? So for each context, they want to figure out an optimal price. So the problem that I'm going to talk about is how to do this, how to come up with pricing policies for such systems in an efficient manner. So one particular application area here is for airline ancillaries. So for airlines offer multiple types of ancillaries: extra bag, seat selection, lounge, fast access, meals, beverages, so on. Now, traditionally, most of the airlines have priced these with static prices, constant prices, right? Baggage has always been sold for $35 in US for most airlines. Now, what airlines are seeing a shift where they are going towards a little bit of unbundling. And so the focus has grown on pricing the ancillaries in a more refined manner. So how does this process work out? In a booking process, a customer selects an itinerary. They enter the information about the itinerary, personal information, so on. And at a later stage, maybe third or fourth page, the airline pitches certain ancillaries to them, right, at certain prices. And then the customer either buys an ancillaries or doesn't. So one particular aspect of this problem is that there is high quality loss information available. So if you have shown a customer an ancillary and they didn't purchase it, that's considered as a loss. In many applications, such information is not available. But in this particular case, it is. So that makes the estimation of purchase probability a little bit easier. So for the airline ancillary problem, the kind of data that we used for building such models comprises of a little bit of traveler features, which includes frequent flyer, tier level, miles balance. But actually, at the end, we didn't decide to use any personal information. So that's why this is grayed out. We didn't use that. Most of the information we used was trip related. So origin, destination, path, departure date, booking date, compartment, so on, right? So these are all trip related information. We also decided to use product features So what's the kind of ancillary? Is it a travel service, in-flight service? What was its historical conversion rate? What is its item popularity score? And so on. So a context is defined as a combination of all of these features. Okay. So the main approach that we used here is reinforcement learning. And as some of the speakers have already said, reinforcement learning is essentially trying to learn an optimal behavior in an unknown environment by repeated interaction with that environment. Right? Now, there are certain problems in reinforcement learning which are hard, particularly the problems which have delayed feedback. So you see a reward signal only after, let's say, 10 steps or 20 steps or unknown number of steps. So that's a delayed feedback problem. Fortunately for us, the pricing problem is not a delayed feedback problem, because if you price, a consumer either buys or not, so you immediately know what is the feedback. Right? So such problems in reinforcement learning literature come under the framework of contextual multi-armed bandits. So these are one episode problems. You put an action. So in this particular case, the action or an R is the price for that ancillary from a discrete set of prices. The state is the shopping context, which I just defined. And the reward, so if you put out an item at a certain price, if a consumer buys it, the price for that paid object was your reward, right? And you immediately get that reward. So these are multi-armed bandit problems. However, and sort of the key trade-off between building these systems is this exploration-exploitation trade-off, right? You want to explore different price points so that you build your model well, but if you do that too much, you will lose revenue. So you want to also exploit the information you have gained so far. Okay. So now there is a key difference in typical multi-armed bandit problems and pricing multi-armed bandit problems. And that difference is that the reward across arms is highly correlated. So what do I mean by that? Suppose you offered a price of $22 to a customer and they bought it. That means that if you would have offered a lower price, they would have also bought it. Similarly, if they didn't buy at $22, they wouldn't buy at any of the higher prices. So these rewards are very highly correlated. In particular, what I'm saying is that purchase probability is the downward sloping curve. So this makes pricing multi-armed bandits a little bit different from the typical multi-armed bandit problems. That is why if you take sort of an off-the-shelf contextual bandit algorithm like LinUCB, you will find that it won't perform well. Even more advanced versions like hybrid linear models with hand-engineered features incorporating prices or squared of the prices because revenue functions are concave show some improvement, but still they leave a lot of gap. Okay. So this is particularly because these models are not able to capture the reward correlation structure that I talked about earlier. So what was so the solution for us was to really encode this model, this downward sloping purchase probability curve into the system. So it's a logistic model. So our observed data is Bernoulli distributed with logistic function as the success probability. But to really do the exploration in a very data efficient manner, you really need to build a Bayesian framework on it. So that means we need to actually learn. So our unknown parameter here are the betas. We really need to, given the data, learn the full distribution on the parameter beta. Right? So therefore, we need a Bayesian framework for this. So if you try to build the Bayesian framework for a logistic model, you quickly realize that it's very hard to compute the posterior probabilities because they don't belong to any conjugate distributions, right? So you tend to use other approaches, other sampling approaches like MCMC, and you realize that these are prohibitively expensive to compute posterior distributions. So instead, we use variational inference methods to construct very fast and scalable algorithm for computing posteriors in this logistic bandit framework. So I'll give a very quick introduction to what variational Bayesian framework is. So suppose you have a posterior on your parameter beta, which is difficult to compute analytically. So what you do is you approximate this posterior by some nice set of distributions denoted by Q. By nice, most of the time people stick to normal family of distribution. And you try to find an approximate distribution by minimizing some notion of distance between true posterior and the approximate distribution. Right, so this is a set of nice distribution, approximating distributions. This is your true posterior, and you're trying to find the best approximation. Right? So the typical measure that people use for minimizing this is the Kullback-Leibler divergence. So you find the parameters of your approximating distribution which minimize scale divergence. Now, so in this particular case, we put a multivariate normal approximating distribution on our parameter beta. And we actually didn't restrict our covariance matrix to be diagonal. It is a complete covariance matrix. And the posterior updates was done using variational Bayes approaches. So if you're implementing, so what we have done is instead our problem of updating posteriors has now converted into an optimization problem. But this is still a slightly difficult optimization problem to solve because this is optimization over almost order d square variables. So if you have 100 features, you're talking about around 10,000 optimization variables. Plus there is this expectation happening here as well. So it's a challenging optimization problem. You could try doing this, writing this out in closed form. So you expand the expectation, take the gradient, and so on. It will be like pages and pages of work. You can publish a paper out of it, but it is still hard. So very recently, like in 2010s, there is this approach called automatic or black box stochastic variational inference methods. So here, what you use is basically automatic differentiation packages like AutoGrad. So Python or PyTorch provides this library, and stochastic optimization to optimize these. So you could interchange the gradient and the expectation operator, and basically once you define in your Python script your likelihood and the approximating distribution, you could basically call the AutoGrad function to compute the gradients. And then because you are taking expected values of those gradients, you do it by sampling. So you use noisy version of gradients there. So this procedure gives you very fast updates, few seconds as compared to minutes in the case of MCMC. Okay, so once you have this posterior update procedure, you could apply your multi-armed bandit algorithms. All these expressions are available because you have the full distribution of your parameter available to you. So either you can implement UCB or you could implement Thompson sampling, which is in practice quite data efficient. So how we tested this method is by building a simulation test bed using real data. So this simulation test bed was derived based on 2 years of transaction history from a real airline customer. So the first thing that you do in simulation is you bootstrap from the sales history transaction and randomly sample a context feature, vector X. Let's say this feature, you're trying to sell Wi-Fi. Your agent prices it at $14. The simulator also has these mean and variance parameters for so the willingness to pay distribution of the consumer. The willingness to pay distribution was assumed to be truncated normal in this case. So once you have this, you sample from this willingness to pay distribution. Let's say the willingness to pay comes out to be 15. So in this particular case, the customer is going to buy this ancillary because their willingness to pay is greater than the offered price. So you could, put your agent in this simulation environment, and by repeatedly interacting with that environment, it will try to learn what the optimal policy is. So next, let me show you some of the results. Okay, so this plot on the left shows you a metric called as relative regret. Essentially, how much off your policy is with respect to the optimal policy. So the optimal policy is the policy which knows the parameter, the true parameter of the model. So in this particular case, a curve which is uniformly lower is better. So it tells you how the relative regret uh, sort of changes with different batches as you get more and more data. So each batch consists of around 500 transactions, and we saw in the sales transaction data 500 transactions on average is like 1 day of transactions. So each batch kind of is equivalent to a day of data, right, in real life. So there are various policies that we tested. The one that I talked about was logistic Thompson sampling with variational inference, but we also compared it to the logistic MCMC policy just to see the goodness of our approximation. So the variational inference based policy is shown in red and the MCMC is in purple. And they are, both of them are the lowest, so they are better than all of the other policies, and they are very close to each other. So that tells you that the approximation that we did with variational inference was very good. The second thing you notice is that starting from, let's say, 16% relative regret, within 15 to 20 batches, you bring it down to around 5%, right? So 15 to 20 batches is essentially 15 to 20 days. So in that amount of time, your system has learned quite a lot, right? Because if you compare it to like a static pricing policy, here the base fare for the ancillary was $40. The relative regret was 15.2%. So given 15.2%, 5 or 3% is much, much better. Okay. So we also see that these off-the-shelf heuristics, the linear UCB and the hybrid linear UCB, do not perform that well. You know, their relative regret about after 100 batches is around 6%, right? So, so I think this method shows a lot of promise in practice. This is just sort of how comparing various prices which are offered, how does it compare to the optimal policy? So the optimal policy is in brown, and we again see that the logistic MCMC, logistic variational inference, are putting out prices which are closer to the optimal prices. Okay, I'll conclude with this. So the main takeaways, again, we considered a problem for ancillary price optimization. But again, this methodology can be implemented in any general pricing setting where the demand functions are unknown either because you don't have data or you didn't do any price variation in the history. The main thing to note is pricing problems have this special structures that the arms or the actions are highly correlated. And you need to really take that into consideration if you want to build good pricing systems. To do efficient data exploration, you need to implement a Bayesian framework. And if you implement a Bayesian framework, variational base could be used for building fast and scalable methods. And as we saw in the simulation experiments, that there is substantial gain if you implement such pricing agents. So with that, I'll conclude, and if you have any questions.